Okay, this lecture will be a brief introduction to the field of particle physics. To begin with, let's start with the fundamental forces of nature. What do we know? Well, you've learned in your introductory physics classes the force of gravity, gravitation. That's the attractive force between objects with mass, for example, between the Earth and the Sun. And we learned Newton's laws of gravitation, or law of gravitation, which is that force is just the product of the masses times Newton's gravitational constant, big G, over the distance squared separating the two objects. Of course, a more advanced course on gravitation would use Einstein's general theory of relativity, where the curvature of space-time, that tensor is related to the stress energy tensor along with Newton's gravitational constant and the speed of light. Okay, we may not have learned that yet, but just to say, there's another description of gravity based on Einstein's general theory of relativity. So that's one fundamental force. You've also learned about electromagnetism, which is the electric force between two objects that have electric charge. And that's embodied by Coulomb's law, which is that it's very similar to the equation above on Newton's law of gravitation. It's the product of the charges over 4 pi epsilon naught. This is the electrostatic constant over the distance squared between those charges, right? We also learned that there's a magnetic force between magnets or between circuits that have electrical currents. Anything that can generate a magnetic field can also give rise to a magnetic force. The Lorentz force law, for example, if you have an object with charge q and has a velocity v in the presence of a magnetic field, this is a vector law or vector equation where the force is q v cross b, the cross product of the velocity and magnetic field direction to give you the direction of the force. It's a little more complicated than the Coulomb force, whose direction would be on the line of sight connecting the two charges. And it turns out the electric and magnetic forces have been unified in a set of equations called Maxwell's equations, where I just show a version of them on the right, which was on a scientific display or memorial, if you like. This is a differential form, so this is the vector calculus form, where you have the divergence of the electric field or the curl of the magnetic field related to changes in time of the electric or magnetic fields. More likely you learn the integral form of Maxwell's equations. But nevertheless, both phenomena are unified by sort of one description. But what else have we learned in this course on modern physics? We also learned that there is a strong nuclear force. This is the force responsible for binding protons and neutrons in atomic nuclei, right? Something had to stick the protons, which had the same electric charge and should repel, stick them together inside of a nucleus, as well as having neutrons which have no electric charge bind together. So this is that force that does that binding, and that the energy in that binding energy, in fact, can be released in nuclear fission and fusion, as you've learned. But still not all forces. There's a fourth one, which is the weak nuclear force. And this is the force that's responsible for radioactive decay. And by that, I mean whereby one particle changes into another type. So not talking about, say, changing by emitting an alpha particle, but I mean changing a proton into a neutron or vice versa. So for example, we learned about beta decay of the neutron, where a free neutron can turn into a proton by emitting an electron and something called a neutrino. So that is the weak nuclear force. So we refer to 4 fundamental forces in particle physics, which also describes the forces as well. Here's a ranking of the approximate strengths of the force. The strong force, named by its name, comes out on top, and we'll give it a ranking 1. The electromagnetic force could be characterized as 100 times smaller, 10 to the minus 2. And the weak force, the coupling is even smaller still. It's 1,000,000 times smaller than the strong force, so 10 to the minus 6. And gravity, the force that we most know about as humans on a planet, it's actually the weakest of all, 10 to the minus 40. Now, these numbers are not just pulled out of a hat. They have some meaning. And you may recall that we learned about the fine structure constant of electromagnetism, which was 1 over 137 as a numeric value, or about 0.01. We could also have written a fine structure constant for each of the other forces, and this is the values approximately that you would get. Strong force being in the neighborhood of 1, weak force in the neighborhood of 10 to the minus 6, and gravity much, much smaller due to the smallness of Newton's gravitational constant. Another thing to point out about this ranking of forces is the strength of the force generally governs the lifetime of unstable particles with an inverse relationship. The stronger the force, the shorter the lifetime typically is. There are exceptions, depending on mass differences on what it's decaying to, but generally, lifetimes that are extremely short probably involve the strong nuclear force. Those that are slow would generally be the weak nuclear force, and electromagnetism in between. And gravity is not included because we're at the particle level. Gravity is so weak, it just cannot be studied particle by particle, really. And in fact, isn't really considered in much of the physics of particle physics, although the dream is to unify it in with the others. Okay, so those were the forces which, if you like, act upon particles of matter, things that we refer to as matter. So let's go about and talk about that. And I'm going to explain to you that it actually is starting to become a zoo. So what have we learned? We actually learned that all stable matter is made of just 3 types of particles: electrons, protons, and neutrons. Right? So we can make up the whole periodic table based on just those 3 particles, as we've seen. However, those are not the only particles. With the advent of particle detectors and accelerators, many other types have been discovered over the past century. We learned about one in this course, the muon, which was discovered in 1938 and has a mass of about a rest mass energy, I should say, of 106 MeV. It's 200 times, more than 200 times heavier than the electron. But shortly after that, in 1947, the pion was discovered, the mass of 135 MeV. And you can see we're learning, borrowing from the Greek alphabet. This was known as the mu meson, and the next as the pi meson. That got a little cumbersome to say. Mu meson became muon, pi meson became pion. But that's not all. In the 60s, the kaon, a family of kaons, was discovered. A rho meson was discovered. An omega baryon was discovered, and even omega meson. And deltas and lambdas and sigmas and xi's. The particles just kept going on. And before we go into this catalog of this zoo of particles, let me show it is possible to see evidence of these particles in experiments. Let me show you the simplest of detectors, which is known as a cloud chamber. It's basically a vapor, an alcohol vapor that's chilled, so it's super saturated. And if you have ionization, it will cause the droplets to condense in that vapor. And if I click on this to get it started, okay, and what you see here are the trajectories of real particles. These lines, some thick, some narrow. They're the ionization trails through this vapor, this cloud chamber. The thick ones are alpha particles, and the skinny ones are actually electrons and some muons. All right, but to talk about this zoo of particles, I invite you to go to this website, pdg.lbl.gov. That's the Lawrence Berkeley Laboratory National Lab. And PDG stands for the Particle Data Group. And they have a listing of all the particles that we know about. Here's an extract for what are known as light, unflavored mesons. Here's our pion, but it comes in several varieties: pi plus, pi minus, and pi zero. There's the eta meson, and a long list of other particles. F's, rhos, omegas, eta primes, a zeros, phi's, and so on. And eventually we just put a number with them to represent their mass. But that's not all. They're the so-called strange mesons, of which the kaon family is a part of, which comes in k plus minus or k0, or even k short or k long, and various other excited states, k stars, k1s, k2s. Or the charm mesons, which include the d mesons, d plus minus, d0, and other higher mass states, excited states, d stars. And even bottom mesons, b plus minus or b0, and excited states as well. But that's still not all. There are particles like the nucleons, the proton and the neutron, which form the lowest mass versions. But they too have excited states, or at least there are higher mass versions of them, which we'll just give by the letter n and their approximate mass. But there are also delta baryons. So the proton neutron are family of particles called baryons. Again, a large variety of those. Lambda baryons, also a large variety of those, and sigma baryons. So obviously, it's a zoo. There are many particles out there. So to tame the zoo, let's try to classify particles here. First of all, let's define hadrons. A hadron is a particle that interacts with the strong nuclear force. So in a sense, you can say it carries strong nuclear charge, because the force, if you can think, might need a coupling to some charge. So particles that interact with a strong nuclear force, like the proton and neutron, are hadrons. But those can be subdivided into those called baryons, which are also known as fermions. That means they have half integer spin, like spin 1/2. The proton and neutron are spin 1/2. So they are fermions with their half integer spin. And they're in the family of baryons, which is a type of hadron. They interact with the strong nuclear force, and they have half integer spin. But also excitations of them, deltas, lambdas, and so on, sigmas, are also in the baryon family. But there are hadrons which don't interact, which don't have spin 1/2, they have integer spin. Those are bosons then, if they have integer spin. They still feel the strong nuclear force, and these make the pi meson, the kaon, the rho, the omega, and they're typically lighter than the baryons, but heavier, say, than the electrons. So they're the middle ground, hence from the Greek, the meso, so it's middle. Mesons are the particles in the hadron category, kind of below the baryons in mass, but heavier than things like the electron. Now, what family does the electron belong to? The electron does not bind in the nucleus. So it is a family of particles called a lepton, those that don't bind in nuclei, and they're all spin 1/2 fermions as far as we know. We don't have an example of a boson. The charged leptons include our friend the electron and its antiparticle, the positron, E plus and E minus. But there is also the mu meson or muon, plus and minus, and there's also a tau meson or tau lepton, plus and minus. And there are electrically neutral leptons. They have no electric charge, and those are the neutrinos, of which it turns out, and we'll discuss more later, that there are 3 types of those. In fact, a neutrino, if you think about it, it has no electric charge, so can't feel the electromagnetic force. It's a lepton, so it doesn't feel the strong nuclear force, so it doesn't feel that force. The only force it feels in particle physics is the weak nuclear force for the neutrinos. And since they have a tiny bit of mass, or at least can have energy, they also interact gravitationally, very, very weakly. Now, it turns out the particles in the first major category, the hadrons, are not fundamental. They are composed of other particles. The leptons are fundamental, that is, they're point-like as far as we know. Haven't found out otherwise. So let's expand a bit on this not fundamental business for the hadrons. And let's do kind of virtually a little activity. So I call this activity the eightfold way activity. And in some sense, we're going to retrace the historical reasoning of physicist Murray Gell-Mann. And it's a card game, or sorting game, I would like to say, where cards will list only the mass and charge of specific particles. And the idea is whether you can see any patterns after organizing these cards by charge and mass. So what are the cards? Here they come in. And all that's listed there is m and a value. That turns out to be the mass of that particle in units of MeVs. And the charge is called Q, 0, -1, +1, in units of the proton charge, electric charge. So you can pause the video here and see if you could sort these by charge and mass and notice any patterns. You know, they're somewhat randomly distributed here, but are there some that could be grouped together? Do you see any features? That's the idea. Right, so these cards can you sort? So go ahead and pause and see if you can think about that. But then now let me just go ahead and sort them a certain way. So let's let the cards move around into a certain arrangement. Same cards. Okay, so what have we done here? Top row, two cards. Mass 940, mass 938. Those are pretty close, right? I think might be similar. One's electrically charged 0, neutral, and one's got +1. Next row, oh, the mass has gone up a bit in MEV. 1197, 1193, 1189. They're not the same, but they're pretty close. They're definitely heavier than the ones above. Apparently there's a negatively charged version, a neutral version, and a positively charged version. Bottom row, 1322, 1315. Those masses are not quite exactly the same, but they're close. Much heavier than the ones at 1190 and heavier again than the ones at 940. There's a negatively charged one and a neutral one. This arrangement, is it telling us something? So that was known as the eightfold way. And let's suppose now that each of those cards that I just showed you are represented by a bound state of 3 particles. So I have to take 3 particles to form one of the cards. And we can take these 3 from a list also of 3 new fundamental particles. So what are these new fundamental particles? One of them let's call U. It has an electric charge of only plus 2/3 e. It's a fractionally charged particle compared to the proton or electron. It's positively charged at 2/3 of the unit of the constant e. There's another particle D. Its electric charge is -1/3 times the value e. So it's also fractionally charged. And another one S, whose charge electrically is the same as the D, -1/3 times e. But S turns out to be a little bit heavier than U or D. Now, you're going to take from this list and see if you can put them together to create the particles that one saw before. Knowing that you've got to add up to the right electric charge. So if my charge was 1, 2/3 is not going to do that. 2/3 and 2/3 would be 4/3 minus 1/3. That would be 3/3. That would be 1. See, I can combine 3 of these in any order I want. They could even all be the same to try to explain. But every time I add an S, the mass gets heavier. All right, let's see what we get. So that can be represented by this diagram here. And it's the same sort of pattern. We had 2 in the top, 3 in the middle. Actually, there's a 4th one stuck in there, and 2 at the bottom again. And some letters underneath them representing the U, D, and S. And those U, D, and S are those new fundamental particles we just proposed. So, for example, we talked about charge 1. I could add 2/3 and 2/3, which is 4/3, subtract off 1/3, and that would be 1. That's what I was describing to you a moment ago. So 2 U's and 1 D could describe the proton, whose mass is 938.3 MeV. What about adding a U, which is plus 2/3 charge, and subtract off by adding 2 negatively 1/3 charged Ds. 2/3 minus a third minus a third is neutral. Mass 939.6 or 940 rounded, that's the neutron. Likewise, for the next heavier row, well, it was heavier. So we better add an S quark. And it turns out there's 3 ways we can do it to have particles that have just one S quark and add up to the charges of -1, 0, or +1. DDS would be all -1, negative a third, negative a third, negative a third. UUS would be like the proton charge 1, and UDS would be 2/3 minus a third minus a third neutral. Heavier still was the bottom row, and that has to have 2 S quarks, and then the third quark can be either U or D. And so I can either have a negatively charged version when they're all charged -1/3, those 3 particles, or a neutral version. And we can see we have names here. The sigma baryons were the middle row, and the X's the bottom row. And so the idea is there's more than just this mathematical game. These UD and S's are evidence for a constituent, a more fundamental particle, which is now called a quark. That was coined by Murray Gell-Mann. And the proton neutron are made of 3 quarks, combinations of an U, which is known as an up quark, and D, known as a down quark. The S is known as the strange quark. So we have up, down, and strange quarks. Describe that. Turns out that's not the only pattern you can make, and those are obviously not the only particles as we've seen. This magazine cover just was highlighting the legacy of Murray Gell-Mann. We just did the topmost pattern, with the neutron proton top and the X's in the bottom and the sigmas in the middle. But there are other patterns to describe, say, the mesons instead of the baryons, and also other baryons down at the bottom. And you get all these different geometric shapes. Kind of cool how they order that way and can be explained. And you may have asked, well, what happens if I had 3 S quarks? We didn't put that one in the above diagram, but it's here at the bottom, it turns out. That omega minus is 3 S quarks. -1/3, -1/3, -1/3. Okay, so we've just now tried to start taming the zoo. There's all these particles, but we can arrange them from just 3 fundamental particles, up, down, and strange. And that should be reminiscent with how we started to explain the 100+ elements of the periodic table. We built them out of just electrons and a nucleus composed of protons and neutrons. We're doing the same thing again for now the particles like the nucleon, but there are more particles than just the neutron and proton that are made of these more fundamental particles called quarks. So that's going to lead us to the theories and the particles that participate, obviously in the universe, in nature, and in this field. And these the theories for the forces and these particles are lumped into something called the Standard Model, which is shown here on the same kind of sculpture at the CERN laboratory, where earlier we focused on the laws of electromagnetism and Maxwell's equation. So this is the Standard Model particles, but let me show you a little bit more carefully on the next slide, this chart. So we just discussed the U, the D, and the S, up, down, and strange. Those were the quarks. But there were more particles than can be described by just U, D, and S. And over history, we learned from experiment that there was a charm quark, a C, a bottom quark, B, and a top quark, T. And this one was only discovered in 1995, so not so long ago to get these ones. The bottom two rows are the leptons, right? These are the ones that don't feel the strong nuclear force. There's our friend, the electron. There's the muon. Here's a tau lepton. And their neutral cousins, the neutrinos. All right. Now, remember the recipe we just learned to build up particles from these quarks. The proton was to take 2 ups and add a down, and that made the proton. Okay. But this chart isn't everything. You also have to add their antiparticles. So there's an anti-up quark, an anti-down quark, an anti-charm quark, an anti-strange. There's an anti-electron known as the positron. There's an anti-muon. It's got positive charge. So we also have the antiparticles, which means opposite charge of the same particle but same mass. But it's also arranged in columns, and it's interesting that matter seemed to have replicated itself 3 times because the electric charge of the up quark was plus 2/3 times the charge of the electron, but so is that of the charm quark and so is that of the top quark. They're all charged 2/3. It's like it copied 3 times. Or the down quark was charged minus 1/3 times the magnitude of the electron charge, but so is the strange, and turns out so is the bottom quark. Same thing for the leptons. There's the electron, the muon, the tau, they're all negatively charged. The only difference seems to be is the mass is changing as you go to higher so-called generations. So we've replicated the first column 3 times, and we're generally going from light on the left side to heavy on the right side, and also kind of going from bottom to top. Or more specifically, from neutrino to top. Turns out the neutrinos are the lightest particles we know about. They apparently have mass, but it's probably well below an electron volt. The electron we know has half an MeV, and then the up and down quarks are around some MeVs, 5, 10 MeV. Charm quark more like a GeV, 1,000 MeV. The bottom quark, 5,000 MeV. Well, 4.2 is what's on the figure. And the top quark, whoops, way off the scale, 171 GeV, which is 171,000 MeVs. Wide range of masses. But that's not all that's on this chart. There's some other particles, right? What are these ones colored in here? Well, you remember the photon from the photoelectric effect. The electromagnetic field is propagated by particles known as the photon. Turns out, the same thing happens for the other forces. The strong nuclear force is propagated by a gluon. But not just one gluon. Turns out there's 8 types. Well, that's interesting. And the weak nuclear force is propagated by particles too, the W plus or the W minus and Z. Also not one type. 2 of them are even charged. So electrically charged. So very interesting there. And the details have to do with the theories of the forces. And there's the latest particle here on the right with the H called the Higgs boson, which was discovered very recently in 2012. And it was necessary for these force-carrying particles. So it turns out the ones that are the quantization of the forces, these two, the last two, the W and Z, actually have mass. The other ones are massless. Gluon and photons are massless. To have those have mass, and in fact to have the particles on the left have mass, we needed a new field and a new particle called the Higgs boson. So it's in there too. Okay, that's a lot there. We'll discuss some of the reasoning that led us to these different types of quarks and different types of neutrinos, for example, and we'll learn a little bit more about the forces in the coming lectures. So that ends this lecture.